Hello everyone. So if some of you have been wondering all this while that when will the kinematics chapter ever end, so it is with this lecture because we are going to start the last topic of the kinematics chapter, and the name of this topic is strain compatibility. Now this topic is a source of a bit of confusion among students. I have seen this happen with many of your seniors. Uh, now, it is for this reason that we are not going to discuss strain compatibility like it is discussed in most of the textbooks. We are not going to present any underlying theory behind it. Rather, we are going to discuss it in a very practical way, like what is the motivation, if at all, for studying this. So, uh, so let's get down to the business of discussing strain compatibility, and we will discuss it in the context of what we have been discussing earlier. So let's go down to our pages. So this is our topic, but we'll first start with a little bit of a recap from one of our earlier pages. So if we go back, yeah, so in one of these earlier lectures we had mentioned this very important set of relations called the strain displacement relations, and these were basically six relations connecting the various components of the strain tensor with the various derivatives of the displacements. So the situation was like this, that if you were supplied with the displacement fields, so you are given how u varies with x, y, z, how v varies with x, y, z, and how w varies with x, y, z, then you can just plug in these formula, use these strain displacement relations directly, and find out the various values of epsilon xx, epsilon yy, epsilon xy, epsilon zz, and so on and so forth. So the similar thing was written in the previous page also here. So here we had written all these things. So if you are given u, v, w in as functions of x, y, z, you can just directly obtain this epsilon xx, epsilon yy, epsilon zz. All that is fine. The question that we want to answer today is, let's go back to today's page. So the question we want to answer today is, what if we are faced with the reverse problem? So what if we are given the strain field, that is, we are given the various components of epsilon ij, and we are asked to find the displacement components. So the situation is completely reversed now. So earlier you had three variables which were known to you, u, v, and w, and from that you could find out the six components of strain. But now it is the reverse thing, meaning that you know the six independent components of strain. So epsilon xx, epsilon yy, epsilon zz, epsilon xy, epsilon yz, epsilon zx, all those are known to you, and from that you have to reverse engineer, or you need to find out the u, v, and w. So the situation is like this. So because we are facing the reverse situation, you think of it like this, that you have these relations. So I'm writing the strain displacement relations just by reversing the left hand side and the right hand side. So earlier we had written epsilon xx as del u del x. Now we are just writing the reverse thing just to change our orientation. So del u del x is equal to epsilon xx, del v del y is equal to epsilon yy, del w del z is equal to epsilon zz half del u del y plus del v del x, that is equal to epsilon xy half del v del z plus del w del y, that is equal to epsilon yz, and finally half del w del x plus del u del z, that is equal to epsilon zx. Okay, so we have these 6 equations, and you may think that fine, we have 6 equations, we can just go forward and solve this, we'll be able to find it out. But there is a little bit of a problem. You see, you can think of these 6 relations that we have just written down in reverse as 6 partial differential equations. Of course, there are partial derivatives here, so they are partial differential equations. So we have 6 partial differential equations in hand, and the things that you need to solve for are what? U, V and W. So what? So you have 6 equations in hand, but you only need to solve for 3 variables. So it is like an overposed problem, and that is where the problem is. Okay, so I repeat what the problem is. If you are given epsilon xx, epsilon yi, so you put all those things, the various components of strain on the right hand side, and these 6 strain displacement relations, you view them as 6 partial differential equations. But partial differential equations to solve what? To solve the 3 components, not the 6, the 3 components of the displacement variable, so u, v and w. So more number of equations you have than the number of variables, and that is where the problem is. So surely there must be something going on in order to maintain the overall consistency, and the thing that we have to ensure in order to make sure that the things are indeed okay, that is what is referred to as the strain compatibility. Okay, so forget about the whatever the intricate maths might be involved, but practically this is what is the situation. So we have more number of equations than the number of variables we have to solve for. Okay, so since we are discussing the practical aspects of it, let us discuss a little example. So all these things, they are they're referred to the 3-dimensional system. So as a practical example, we can take a simplified 2-dimensional version of the same story, and we can illustrate actually that there may actually arise a case where this, if you're given any arbitrary sort of values of the strains, it may not lead to a proper set of solutions for the displacement variable. Okay, so I'll illustrate to you a so-called incompatible strain field. Okay, so illustration of an incompatible strain field. So I'm telling you that this is going to be incompatible. Okay, it's like telling you the result of a detective story before telling you the story. But anyway, so let's say we have epsilon xx is equal to y square, epsilon xy is equal to 0, and epsilon yy is equal to 0. This is what is given to us. So let's write this. It is given to us. This is given, and question is that you find u, v and w. Okay, so what can we do? Well, at the very outset, we can start with this epsilon xx equal to y square. So because we are interested in finding out the u, v, w, you just check from these reverse strain displacement relations that this del u del x is equal to epsilon xx. That is perhaps where you need to that is what is perhaps you need to use first of all to perhaps obtain some expression for u. Okay, so we are going to do that in the next page. So what we have is del u del x is equal to epsilon xx is equal to y square. Now this is a partial differential equation, and we can solve this. So what do we need to write here? So had this been a simple or an ordinary differential equation, then you could have just put a constant of integration here, but this is, mind you, a partial derivative with respect to x. So the only thing that we could perhaps write here is that this will be some unknown function of y. So this f of y, this is a pure function of y. This f does not have any dependence on x. Right now we do not know the form of f, so we'll investigate this. Now we have some form of u. Now what we can do is we can try to use the rest of the information that is given to us. So you go back here and you note the epsilon xy is equal to 0. You also note that epsilon yy is equal to 0. So del v del y, that is equal to epsilon yy, and that is given as 0. So just like before, what we can do is we can find out v as some function of x. All right. So from this expression of u and this expression of v involving the unknown pure functions of y and the pure function of x, we can find this epsilon xy is equal to half del u del y plus del v del x. And if we do this, if we actually substitute these expressions of u and v here, what we will obtain is half of, so the del u del y from here, it will give us twice xy plus df dy. Please note very carefully that I am not writing a partial derivative here. This is an ordinary derivative because f is a pure function of y. Okay, for the del v del x, we just need to write down dg dx. This is dg dx, not del g dx, not del g del x. This is dg dx, again an ordinary derivative. Okay, so now we can compare the given information. What is given to us? Epsilon xy is given to us as 0. So but epsilon xy is given to be 0. Therefore we must have half twice xy plus df dy plus dg dx is equal to 0, or you can just remove this half here. So what we have is twice xy plus df dy plus dg dx is equal to 0. This is where things get critically important to look carefully. You see, So this is some sort of an equation with the right hand side as 0. You also note that f is a pure function of y, which means that df dy is at best a function of y. G is a pure function of x, so dg dx is at best a pure function of x. It could be a constant, this could be a constant, but no matter what you do, it cannot happen that just because you do a derivative with respect to y, somehow magically some kind of x dependence will emerge here. Similarly, no matter what you do here, after the derivative of after you have taken the derivative with respect to x, it simply cannot happen that a dependence on y will magically emerge here. So this thing will still depend on y, this thing will still depend only on x. At best, what can happen is that this thing will turn out to be a constant, this thing will turn out to be a constant. Other than that, nothing else can happen. However, this thing is sitting. This is the problematic part, the twice xy. Okay, so no matter what happens here and no matter what happens here, this overall equation, you please note very carefully that this overall equation can never be satisfied. You see, suppose this were a pure function of y and this were a pure function of x. Okay, then certainly this equation cannot be satisfied. Alright. Furthermore, suppose this were a constant. Suppose f is like some ky, and suppose this g is like some cx. So after the first derivative with respect to y, this will give you just a simple constant k, and this will give you a simple constant c. And then suppose if this twice xy was not present, then you could have obtained as a nice equation that k plus c is equal to 0. That could have been satisfied. But no matter what you do here, this twice xy is always remaining there. So this equation, this equation can never be satisfied. And the problem is with the twice xy part. Okay, the problem is with the twice xy part. Now you just imagine for a second, okay, just imagine for a second that the twice xy part was not there. Just hypothetically, you imagine that if twice xy were absent, then the equation you have in your hand is df dy plus dg dx is equal to 0. Now this thing that we have here, that one of the terms is at best a pure function of y and the other one is a pure function of x, this is somewhat reminiscent of what I believe what you may have come across in your fluid mechanics course, so where you had an equation like the gradient of the pressure, the dp dx on the one hand in one of the terms, and on the other hand you had in another term the mu d square v vx dy square. So one of them, the term involving the vx, was a pure function of y and the pressure was a pure function of x, and the way you proceeded in that equation, so I believe this was covered in the topic some exact solutions, you proceeded with the argument that since one of them is a pure function of y and the other is a pure function of x, and on the right hand side is equal to 0, so the only way this can be possible is if, and similarly here, that df dy is equal to minus dg dx is equal to some constant k. The only way this is possible is like this. But you see, this is true only if the 2xy were not there. But here 2xy is very much present here, because this basically follows from the strain field that was given to us. So because we have arrived at a situation where the strain field given to us and the information that we are deducing from the obtained displacement field forms from u and from v, whatever form of epsilon xy we are obtaining, there is a mismatch. Okay, that is why we are saying that this is an incompatible strain field. I repeat, this is given to us rather arbitrarily, but it turns out that if we use epsilon xx and epsilon yy, then the forms of u and v we end up with, it gives rise to a form of epsilon xy like this, which is simply cannot be equal to this particular form, and that is why this is an incompatible strain field. So with that, I believe I have covered whatever I wanted to cover in this topic, and as promised, with this we end the kinematics chapter. Now the next chapter will be dealing with stress, and it is there that we will be concerned, unlike the kinematics chapter, with the loadings, the forces and everything that actually brings about the displacements and gives rise to various sorts of strains, and in the chapter next to that we'll be discussing the connections between stresses and strains. So all right, thank you very much.